Hi everyone, this is Mrs. Pettit one more time, here to talk to you today about growth and decay, which is another application of exponential equations. Let's start by talking about the graphs of exponential growth and decay, and I'm just going to write this in a little better format for you. So one example of growth would be y equals 2 raised to the x power. And one example of decay would be y is equal to 2 to the negative x power. Just so we can look at the graphs and think about some similarities and differences. So you may notice some similarities, such as they have the same basic shape. They have the same y-intercept at y equals 1 in this case. And they both approach the x-axis. Something you may notice that's different is that growth moves away from the x-axis. As we move from left to right. And decay moves towards the x-axis. As we move from left to right. And if we focus on why these graphs don't cross the x-axis, let's go back to what we first learned when we started talking about logarithms. So if we look at growth in exponential form, and we change that to log form. So if I have y equals 2 to the x, in log form that becomes log base 2 of y equals x. And remember, when we started talking about logarithms, we said the argument must be positive. In other words, y has to be greater than 0. And now, looking at these graphs, we can really see why. So yesterday, you learned about how money invested grows exponentially over time. There are some other things that either grow or decay exponentially, and they include things like populations, or bacteria, or diseases, just to name a few. And very similar to your interest formula for compounding continuously, the growth and decay function is A equals NE raised to the power of K times T, where we see that E again, right? So it looks very similar to your PERT formula, or PE raised to the power of R times T, where in our case, A is the total amount after time, so that's exactly the same as what you used it as yesterday. N is the initial amount, or what you start with, so that was similar to P, right, or your principal, what you started with. K in our case is the growth or decay rate, again, as a decimal, so that's similar to your rate, or R, from yesterday. And again, T is time and can be in any measurement of time. So that's exactly the same as how you used it yesterday. You'll notice that the formulas are very similar, right? And again, you'll see that E is present, which means we're going to use natural logarithms when we're trying to solve for particular parts within the growth and decay function. So let's walk through a couple of examples using our new growth and decay function. I'm just going to put it up here on the top of the page so that we have it to look at, And then as we go through each problem, we'll try and pull out each piece of information that's given so we know in the end what we're trying to look for. So we'll put that formula up there, A equals NE raised to the power of K times T, and read the first problem. In this case, we want to solve for T. It's telling us flat out. So we need to find A, N, and K somewhere within the problem. It says, in the last census, the Darien population was 20,732. If the population grows exponentially at a rate of 3.4% per decade, how many years, so we're going to have to be careful when we find our answer, will it take for the town to reach a population of 25,000? So I'm just going to put each one of the variables over here to the left and fill in what I know. So A is where I'm trying to end. So A is 25,000. N is what I start with. So the population I started with was 20,732. K, remember, has to be input as a decimal. So 3.4% is going to be 0.034. And T, the time, is what we're looking for. So if I just start plugging in the information that I know, I have 25,000 equals 20,732. E to the 0.034 T. The first thing I'm going to do to start solving is divide by 20,732 to isolate the exponential part of the equation. So 20,732 divide both sides. I'll end up with 1.205, and it continues on the calculator. So I'm going to put this little ... here to say I'm going to keep that number on my calculator and go back and use the entire number so that I don't get too much round off error. And then on the right hand side, I will have E to the 0.034 T. Because of the E, we're going to take the natural log of both sides. So I'll have the natural log of 1.205. And again, the ... to tell me, go back and use what's sitting on my calculator. The natural log of E to the 0.034 T. When I put the natural log of this number into my calculator, I get 0.187. And again, there's more sitting on the calculator, and I'm going to keep it sitting there. Remember, our rules for exponents are to pull that exponent out front, which will give me 0.034 T, and the natural log of E is just 1, so I don't need it in this case. So now I'm going to divide by 0.034, and I'll find out that T is equal to 5.51. Now go back and remember what we had from the problem. It said 3.4% per decade, so our time is in decades. But it says how many years will it take for the town to reach this population? So we want to multiply by 10 so we know how many years from now. And that'll be in 55.1 years. The population in Darien will reach 25,000. Let's take a look at the next example. It also says that we will be solving for T. But let's read through the problem and see if we can find what we know about the other variables. Because the polar ice cap is receding, the habitat for the polar bear is decreasing, and thus the polar bear population is decreasing at an exponential rate of 1.8% per year. So decreasing, that means that our K value is going to be negative, and again, needs to be as a decimal. Today there are approximately 25,000 polar bears, so that's where we're starting. And if the trend continues, when will there be only 2,000 polar bears left? So again, we'll start plugging in what we know. So 2,000 equals 25,000 e to the negative 0.018 t. Divide both sides by 25,000 to get the exponential part of the equation by itself. And on the left-hand side, I'll have 0.08. And on the right-hand side, I'll have e to the negative 0.018 t. Taking the natural log of both sides allows me to eliminate e in the equation. So the natural log of 0.08 is negative 2.525. And again, that's not all that my calculator says, so I will make sure to go back and get all of it. And when I bring the exponent out front, I have 0.018t, and the natural log of e is just 1, so that disappears. When I divide both sides by 0.018, then I find out that the polar bear population will be down to 2,000 in 140.3 years. So we've solved one problem for time where the value of k was increasing, and we solved for time in one case where the value of k was decreasing. Now let's try and see if we can solve a problem where we're actually solving for k. So solve for k, or the rate of growth or decay, if your lawn is being overrun by weeds. If in 2010 you had 5 million blades of grass, and today you only have 57,000 blades, what is the rate of decay? So we know how many we end with. We know how many we started with, right? We end with 57,000 and we start with 5 million. Our rate of decay is what we're looking for if our time is 10 years, right? 10 years because this year is 2020 and we had 5 million blades in 2010. So again, just plugging into our equation, we have 57,000 equals 5 million e to the k times 10. So again, to isolate the exponential part of the equation, the first thing I'll do is divide by 5 million. And the left-hand side becomes 0.0114, and the right-hand side becomes e to the 10k. Taking the natural log of both sides leaves me with negative 4.474, and again, there's more information on my calculator. Pulling the exponent out front and knowing that the natural log of e is 1, dividing both sides by 10 leaves me with a value for k of negative 0.447, which means that the blades of grass in my lawn are decreasing by 44.7% each year. And in the last example here, we want to solve for n, or where we start. So it says, Mrs. Pettit arrives in her classroom to find a bologna sandwich has been abandoned for 7 days. If the rate of growth for the bacteria on the sandwich was 10.2% per day, and she finds there are 7,200 bacteria on the sandwich, how many bacteria existed on the sandwich to begin with? So we're looking for that starting value if we know we end with 7,200. Our K value will be 0.102 and our time is 7 days. So again, plugging in what we know. I'm looking for N this time. E to the 0.102 times 7. Now we can just plug that into our calculator. So I'll have 7,200 equals N. There's an E button on your calculator. It's the second function of the natural log button. And then you can just type in 0.102 times 7 in the exponential portion, and then close the parenthesis and hit enter. And you'll find that E raised to the 0.102 times 7 is 2.042, and again, more information on my calculator. So if I divide 7,200 by that entire value, I'll find out that a number of bacteria that started on the bologna sandwich was 3,525.7 bacteria. And I'm okay with leaving that as a decimal. Originally, it probably started with some whole number value of bacteria. But the point where we're talking about it 7 days in, it may have already been growing, so there could be the possibility that it was in the process of growing a bacteria. So I'm going to leave the answer as 3,525.7 bacteria. At this point, there are a few more extra practice problems for you to try, and then check against the solution key.